In this section, we're going to look at the mathematics of operating a camera. The important equations for camera, in addition to our lens equation and magnification equation, are the F number is very camera specific, and when we're looking at doing an exposure, we're looking at the total amount of energy that we put onto the film. This will be our target to get it properly exposed, not underexposed, not overexposed, and that depends on the power of light that we're getting, and that depends on the power getting to the camera depends on the intensity of light naturally and the area or the aperture size that we're dealing with. Now we're going to look at an example where we use all of our camera equations to figure out the problem. So here we have a person on safari. It would love to go on a safari, takes a photograph of a hippopotamus. That's very dangerous from a distance of 75 meters. Hopefully that's far enough away, but that distance means that that's our P value. The animal is 4 meters long, that would be H, and the image is to be 1.2 centimeters long. That's our H primed, and that's really a negative 1.2 centimeters because the image will be real and inverted because we want the hippopotamus image to be inside our camera on the other side of the lens, safely tucked away for future viewing. We're going to use then our magnification equation to use our H and H primed to go from P to Q. Solving for Q then gives us negative Q is equal to H primed over H times P, and we are given all those values, put a negative sign up front, negative 1.2 centimeters over 4 meters times 75 meters, all given in the problem. And we get negative 22.5 centimeters, noting that these 2 meters cancel, and I'm left with centimeters. Now then, I can use my lens equation to figure out what the focal length is. So we already figured out that P was 75 meters, plus 1 over Q is negative 0.225 meters. Notice that I'm using meters for both of these, and that gives me a focal length of 22.47 centimeters. Next thing I want to do is what size of image would we have if we switched to a 50 millimeter focal length lens. So we're just going to run those equations in reverse. So we get 1 over Q is equal to 1 over F Q minus 1 over P, so I get 1 over 50 minus 1 over 75 times 10 to the negative third millimeters. That's positive 3 because we're 75 meters away, and I'm using millimeters because I want my Q in millimeters at 50 millimeters. This is basically infinity. So you notice that this number and this number are the same because this number is really, really big compared to 50, and so for all effective purposes, it's infinity. Okay, then we want to calculate H primed is equal to negative Q over P times H gives us 50 over 75. That's negative times 4.0 meters is our original hippo length, negative 2.67 millimeters. So the negative sign means that we have a real image and that it is inverted, which we would expect to be able to place that image on the film. Now we're going to look at changing our exposure. The initial exposure we said was corrected at f16 and 1/16 of a second. Now we want to change our aperture, presumably because we want to have a shorter depth of field and have a more stylistic picture. So we need to figure out what time we would need to give us the same exposure. So the goal for the same exposure is to have the same energy level being collected on the film. And we know that the energy level is equal to the power that I'm sent to it and the time. And how is that related to then my aperture? So these are the three equations we're going to combine in order to come up with a relationship between time and F number. The first step, we're going to look at how the f number is related to the diameter. Presumably we're using the same focal length lens, so what I'm going to use is a series of relationships to figure out what my ultimate relationship should be. So f number initial over f number final is equal to, basically I'm using this equation, f over d initial divided by f over d final is equal to d final over d initial. And that's going to be equal to 16, which was my original f number, divided by my final f number, gives me a value of 2.857. And this is again initial over final. And so that means that d final is 2.86 times d initial. Okay, and we were able to cancel out the f's because presumably we're using the same lens, so therefore that number is constant. Okay, the next thing we want to do is use our power relationship, u is equal to power times time. So power final over power initial is equal to IA final over IA initial. And the intensities, light intensity is the same. So we didn't change the settings. We didn't go to a suddenly inside from outside. So I stays the same. That means A final over A initial. And area is equal to pi over 4 d final squared and pi over 4 d initial squared. And these are all constants, so they cancel, so I get d final over d initial squared. And we just figured out what that value was. That's at 2.857 squared is equal to 8.163. That means that the power coming through the larger opening is about 8 times more power than the smaller opening. Okay, now we're going to use our final equation that we need in this set, and that is that power is equal to energy over time, or energy is equal to power times time. So I get that 8.163 is equal to power final over power initial, was a result I just got from the last one, and I'm going to substitute u over t final over u over t initial. And again, we want the same exposure. So we're going to cancel those out. T initial over T final. That means now I have my final relationship. T final is equal to T initial over 8.163, or this is equal to 0.1225 T initial. So that means I only need about 12% of the time. And we said our initial time was 1225 was 1/16 of a second. So that gives me a new exposure time of 1/360th of a second. So it shouldn't be any surprise that I have a bigger opening. I need a shorter amount of time. This then gives us a general relationship that the ratio of the times is equal to the ratio of the f numbers squared. And since we've derived this equation, this is now an equation that you can use and write down. It's a general equation. So generally, a 2fx number will require 4x the amount of time. Now we're going to look at a little simpler problem, one that's more indicative of what you would see on homework or an exam. So here we have a camera with a 200mm focal length lens, and the lens and film distance can be adjusted from 200 to 210. And we want to figure out what's the closest an object can be placed to get a clear image. So the first thing to do is figure out which one of these numbers we want to deal with. Well, since the focal length is 200 millimeters, these are our Q's, then if something is at infinity, then it's going to be at 200 millimeters. So the number we really want to look at for something that's closer is 210 millimeters. So here's our basic lens equation. Solve for 1 over p. So that's what I want to solve for. So we get 200 millimeters minus 210 millimeters gives us a p of 4,200 millimeters, or 4.2 meters. That means we're dealing with something that's still pretty far away, and most likely this is a telephoto lens, because even a 1 centimeter change of distance from our camera's lens to our film is pretty big. So this is going to be a pretty long lens and pretty telephoto. Then what aperture diameter would result in giving this lens a rating of an f16? Well, we're going to look at our f numbers and rearrange it. So my diameter is equal to my focal length divided by my f number. That's going to be 200 millimeters over 16 equals 12.5 millimeters for that diameter.